All right. So, in the last class, we were discussing about. We started discussing about the IV characteristics. Um, so, so basically, what you did is we derived the IV characteristic when Vg is greater than Vth, right? So the Vg is greater than threshold voltage. So when your gate voltage is more than threshold voltage, so we have a sheet of electrons sitting at the silicon dioxide interface. We call that sheet of electrons a channel. Then if you apply the voltage across this sheet of electrons, these electrons will start moving, right? So here I have drawn the inversion layer, that the channel. So the channel, the whole inversion layer or whole channel has a width of W, a length of L. That is the gate length L, um, and a thickness of inversion layer thickness T inversion, right? So from so to derive the current, so basically this current is because of drift, right? So here, so if I take a smaller region, right? So let's say I take a smaller region dy, and dy and this direction is y, right? So this direction is y. So the voltage across this small region dy is dv, right? And so your drift velocity. So basically, what I'll do, I'll calculate the current in that small region. Then I can integrate, right, from 0 to L, right? So your drift velocity in that region, small region is um, mu times electric field, and the electric field in the y direction, and the electric field in the y direction is if the voltage drop is dv and this region is dy, so your electric field is dv by dy. So vd will be mu times dv by dy. Mu is the mobility of the electrons, right? So the time required to go from position 1 to position 2, right? So this is position 1 and position 2. So is nothing but it will be dy times drift velocity. So okay, so this is the time, right? So the total charge in this small region. So total charge in this small region, this dark yellow region, is if you take the n. So if you look at, so this is the total number of electrons. The charge is q times n. So then the volume, right? The volume is w times dy times t inversion, right? So this is the volume. All right. So this is the total charge. So this unit here is coulomb, right? Unit here is coulomb. Okay. So now if I take the I could write this total charge in coulomb to q inversion, when it's like q inversion is inversion charge per centimeter square into some factor, right? So if I see here, right? So if you go from the q inversion term, right? So q inversion term, right? So basically the area, the surface area of this small region is w times dy. So q inversion is nothing but q n t inversion, right? So this is coulomb per centimeter square, right? This is coulomb per centimeter square. So then I'll replace this q n t inversion by this q inversion, that is per centimeter square. So I have this q inversion times w times dy. So if this is the total charge, the current is charge, total charge divided by the time required to go from point 1 to point 2. So this is dy by d, means time is dy by vd, the drift velocity, right? So if I do that math, then the current will be q inversion w times vd, right? And so this is the current in this small region, right? So, and if I could write that, so I means previously we had written q inversion. So q inversion is Cox times Vgs minus Vth minus Vy. So Vy is the voltage in the y direction, right? So if I do that, then if I want to find the total current, then I have to integrate it from 0 to L, and the right hand side I have to integrate from 0 to Vds. So if I do this math here, the integration, and I put the limit, then so basically my drain current will be mu Cox double by L VGS minus VTH into VDS minus RVTH, correct? So this part we had done in the last class. So so here from this equation, so this is the basic current equation in a MOS transistor. From this equation, you could see the drain current is a function of gate to source voltage, drain to source voltage, width, length, oxide thickness, and mobility, right? So your drain current is a function of most of these things. But if once your technology is fixed, right? Once your technology is fixed, your Tox is fixed, is mu is fixed. So then your ID will be function of VGS, VDS, W, and L, right? So W by L you could always choose, and by applying different VGS and VDS, you could get different current, right? So this part we had done in the last class. So now, if I take this equation and plot as a function of ID, right? So I'll plot this equation. So in the x-axis I have VDS. So x-axis I have VDS and y-axis I have ID, drain current. So this is ampere, this is volt, right? So you see, this is a parabolic curve, right? So if I plot it, the shape will be like this, right? So it will initially increase, then at certain current, right, and certain VG, right? So this is my, let's say VGX. At certain VGX, sorry, not VGX, right? So this is VDX, right? At certain VD, your curve will again go down, right? So this is means if you take this curve, take this equation and plot it, ID as a function of VDS, right? So and this point here, right? This VDX, you could find out at VDX because your ID is maximum. That means your at VD equal to VDX, your did by dVds will be 0, right? So this is 0. So from here, if I do that, then you'll see that your VDX is nothing but VGS minus VTS, right? So this point here is nothing but VGS minus VTH, and many times we call it overdrive voltage, right? So we call this VGS minus VTH is overdrive voltage. So this just tells you means what is the means this just tells you the difference between VGS and VTH. So this tells you how high VG you are applying above threshold voltage, right? So this is the overdrive voltage. Okay, so this is the nature of the thing, right? So if you take this equation, then plot ID as a function of VDS, you will get a parabolic curve, right? And so your current will initially increase, then decrease, right? And that maximum current will happen at VGS minus VTS, right? But if means, but this, so basically what is telling that as you go on increasing VDS, your current will increase, then it will decrease, right? But it is not very sure, right? So why my current will decrease? Because my VGS is constant. So this is at a constant at a particular VGS. My VGS is constant. That means I have electrons in the surface. If I go on increasing VDS, why my current will decrease after some time? So that means this curve does not give you the means this equation doesn't give you the full characteristics, right? Okay, so let's see what happens when you go on increasing the drain to source voltage, right? So if you look at the immersion layer, right? If you look at the immersion layer, so when VD, let's say if VD is small, right? So okay, so if VD is 0, right? So this inversion layer is uniform, right? So uniform in the sense the from source side to drain side. So you have a inversion layer. The thickness of the inversion layer is uniform because that is so when the VD and VS both are 0, right? Right, and you are applying a gate voltage side better than VTH side, right? So okay. So we know that this Q inversion, so means Q inversion as a function of y, because this is the y direction. So this part we have derived. So this will be Cox means VGS minus VTH minus Vy, right? And how is your Vy varying? So if you look at your Vy, so Vy is so this is your y and this is Vy. So your Vy, right? So this is your VDS, right? So basically your Vy is varying from 0. So this is the source end, this is the source end, and this is the drain end. So between source and drain, your Vy is varying from 0 to VDS, right? Okay. So so in this case, right? So in this particular case, when your source and drain both are 0, so your Q inversion in the source side when y equal to 0 is Cox VGS minus VTH, right? Right? And Q inversion at the drain side, right? This is also Cox VGS minus VTH, because uh, you see when both are 0, right? Right. So your source is at 0, drain equal to 0. So your Q inversion is uniform, right? So your inversion layer is uniform from source side to drain side, and the value is Cox minus VTH. If I want to write down what is the total Q inversion, so total Q inversion equal to Cox VGS minus VTH, Cox VGS minus VTH into W times L, right? So this is total Q inversion. Um, this is Coulomb, right? Right. So this is Coulomb, right? Okay. Okay. Now, right. So let's say I apply a VD, I apply drain voltage, right? So drain voltage is positive, right? So your VD1 is positive. There will be some drain voltage you are applying, right? So your VD is positive. So when your VD is positive, that means so when your drain voltage is positive, so your reverse biasing your source and drain junction, right? So if you look at this junction here, so so this sorry the drain and body junction. So this junction, because your body is at ground, so when you're applying some drain voltage, so you are reverse biasing your drain and body junction, right? So the drain and body junction. So when you reverse bias, right? So your depletion width, right? So basically your depletion width in the drain side will increase, your depletion width in the source side will remain same, because source side anyway is grounded, right? So what will happen, right? So if you could see here, right? So let's say in the beginning VD1 is 0, so you had uniform, so your depletion layer is like this and your inversion layer is uniform. Then if I apply VD2 is some positive value, right? But positive value here. So what will happen? Your drain side depletion width will increase, right? So so you see, so when I'm applying some gate voltage, that means I have some gate charge, right? So I have some gate charge, right? And total gate charge equal to at any point, right? Any point means QG at any y equal to Q inversion. Better to start with Q depletion at any y plus Q inversion at any y, right? So so if you see, um, if what is happening here is, so if my VD2, if I applying some positive drain voltage, that means your depletion charge in the drain side is increasing, because the drain body junction is becoming more reverse bias, more and more reverse bias. So the depletion charge in the drain side is increasing. If QD is increasing, right? Because your QG is constant, so Q inversion will reduce, right? Right. So you will, as you go on increasing your drain voltage, so you will see that inversion, the inversion charge per centimeter square, right, in the drain side, right, will slowly decrease, and at some VD, so this inversion charge will become zero at drain side, right? So as you are written down, right? So let's say we have done this Q inversion Y is Cox BGS minus BTH minus By, right? So you know, right? So V 0 is 0, and but V at L, that means drain side is VDS, right? So Q inversion in the source side is will be Cox minus BGS minus BTH, but Q inversion in the drain side will be BGS minus BTH minus VDS, right? Minus VD, minus VD, right? So at VD VD equal to VGS minus VTS, right? So as you're going on as you go on increasing your drain voltage at some VD, your Q inversion in the L side will be Cox VGS minus VTH minus VGS plus VTH. So this will be 0, right? So this voltage where the because you see if I come here, right, come back, so here you see at if I apply VGS minus VTH here, right, if my VD is VGS minus VTH, right, if my VD is VGS minus VTH, so at the drain side your inversion layer thickness on the drain side will be 0, right? Your inversion charge in the drain side will be 0, and that point we call the pinch off, and this condition we call the pinch off condition, right? That means your channel is pinched off, right? So you do not have a continuous channel between source and drain. So at the drain side, your channel thickness of your inversion layer is becoming 0, right? So that means your just channel is pinched off, right? Right. So what will happen if I apply your apply drain voltage above VGS minus VTH? So if I apply drain voltage, so this is 0, and let's say this is VGS minus VTH, and this VD3, if VD3 is more than VGS minus VTH, that means your pinch off point will move, right? So because your voltage is increasing, so your pinch off point will move, right? Pinch off point will move towards source, right? Please keep in mind, so the voltage, right? Your voltage at the pincher point is always VGS minus VTS, right? So your voltage here is always VGS minus VTS, right? Right. So let's say this is my pincher point volt. So this pincher point, and voltage at the pincher point is always VGS minus VTS, because the charge will become 0 when your voltage becomes VGS minus VTS, right? So that's the at the end of inversion layer, right? So your pinch off point is nothing but the end of the inversion layer, right? At end of the inversion layer, so your voltage is always means VGS minus VTS, right? So your means your so the pinch, so at the pinch off point, the voltage is always VGS minus VTS, right? So if I take this, right, so let's see, right? So so if I take this, right, so you see here, um, so what is the average? So basically, your inversion, so this is my 0 because y equal to 0 here, and y equal to L here, right? So this is 0, this is L, and this is the pinch off point. So Q inversion at 0 is nothing but VGS Cox times VGS minus BTH, right? Um, right. So if I multiply by W times L, this will be so So if I multiply W, this will be total Coulomb charge, right? Okay. So similarly, Q inversion, let's not multiply, right? So this is for centimeter square. This is Coulomb per centimeter square, right? Similarly, Q inversion at L is 0, and Q inversion at the pinch off point, let's say P, this is again 0, right? So so you see, when VDS is more than VDS equal to VGS minus VTS, your channel just pinched off, right? But the pincher point is at L, right? But when VDS is more than VGS minus VTS, your pincher point has moved towards source, right? So let's say this is some delta L, right? So basically, if delta L, I mean, if delta is much less than L, right? So let's say you have a very long channel, right? So you are talking about very long channel transistor, your transistor is very long. So this delta L, the little bit shift in pinch off voltage is much less, right? Delta L is much lesser than L, right? So in this case, if you look at the total inversion charge, right? Average inversion charge, right? So see, you see, this is a so at 0 is Cox VGS minus VT. So this will be nothing but, I could write down the average inversion charge is half Cox, because one in the left hand side I have Cox VGS minus VTS. In the right hand side I have 0. If I take the average inversion charge, this is nothing but half Cox minus into VGS minus VTS, right? And if I want to find what is the total inversion charge, then I could multiply by multiply into double by L, right? Multiply this into double by L, right? So this is Coulomb, right? And this is the average, right? So you see, if your delta L is less than L, so after VDS, if VDS is more than VGS minus VTS, the average inversion charge is always half Cox VGS minus VTS, right? That means what is happening is, okay, so okay, so coming back, when VD equal to 0, your average charge is Cox times VGS minus VTS, right, in the channel, right? Because source side you have Cox VGS minus VTS, drain side you have Cox VGS minus VTS. It is a uniform, so the average charge is Cox times VGS minus VTS, right? When VD equal to VGS minus VT, the average charge, because your source side is Cox times VGS minus VTS, your drain side is 0, so average charge is half Cox VGS minus VTS, right? And but in the but when VD is more than VGS minus VTS, assuming that this delta L is less than L, so this is still half Cox VGS minus VTS, right? So what is happening? So if you look at this thing, right? So after pinch off, right? So the moment your channel is pinched off, your inversion charge is remaining constant. Your inversion charge is not changing, right? Okay. So this is one thing. Other one is because your current. If I look about current, right? So your current, right? So when I talk your current is nothing but charge into velocity, right? Your current is charge into velocity, and this is the inversion charge. And velocity is nothing but mobility times electric field, right? Or mobility times dV by dy, right? So again, if I look at dV by dy, right? So dV by dy. So in this case, right? What is dV by dy in the first case, right? So I have a channel, and what is the voltage difference across the channel is 0, and dy, so this is 0 by L, so I could write down this is 0, right? In the second case, right? In the second case, your dV by dy is the voltage across the channel is VGS minus VTH, VGS minus VTH divided by L, right? Similarly, in the third case, your dV by dy is VGS minus VTS divided by L again, because I told you, right? So your pinch off point, voltage at the pinch off point always VGS minus VTS, right? This does not go beyond VGS minus VTS, right? And and if your delta L, so this should be L minus delta L. But if your delta L is less, then you could still write it as Vgs minus Vts by L, right? So what you're observing that the moment your channel is pinched off, your electric field across the channel is also remaining same, right? So your this, so basically what first I told, okay, once the channel is pinched off, your charge is remaining constant, and also when the channel is pinched off, your velocity is remaining constant because mobility is constant, your electric field is constant. So your then the moment your VDS equal to VGS minus VTS, right? So after that, your current will remain constant because your charge is constant, your electric field is constant, right? Right. So if I come back to this graph here, right? So right. So if I come back, let me copy this. Okay. So right. So the moment, so basically, what am the when the VDS, if VDS is more than VGS minus VTH, your current will remain constant, right? Because as I told you, so your if VDS equal to more than equal to VGS minus VTH, right? Your inversion charge is constant, and your electric field is constant, right? Is also constant. So, but this is assuming that your delta L is less than L, right? Right. This is assumption, right? So if your inversion charge is constant, your electric field is constant, your current will remain constant, right? So that's the reason at when your drain voltage is VGS minus VTS, so there your current saturates, right? Then it stays constant, right? And this portion we call the means, so basically then we could because your current equation should change because this part we call saturation because your current saturates. So this is unlike your bipolar junction transistor. Bipolar junction transistor, when the current saturates, we call it forward active mode, right? And other part is your saturation, right? Right. But in this case, when the current saturates, we call it saturation region, and the saturation, the transistor will go into saturation when VDS more than VGS minus VTS, right? And the other part, this part here, this is called the linear because if you look at lower VDS part, so lower VDS part, um, your your current is linearly proportional, right? So basically, if you look at small VDS, your current is linearly proportional to ID. ID is linearly proportional to VDS, right? So we have three conditions here. So first one is cutoff, right? Cutoff is when your VGS is less than VTH, right? And VDS, any VDS, right? Doesn't matter, right? Any VDS, right? So cutoff condition is when your gate to source voltage is less than VTS, right? That means uh, less than VTS means you do not have any inversion layer, right? So that is your cutoff, right? Your transistor is off, right? So basically here if you see, I have done VGS less than VTS, right? Right? VGS is much less than VTS, right? That means VGS is very close to 0 volt, right? Right? That is cutoff condition, right? If VGS is less than VTS, VGS is positive but less than VTH, we have some small current flowing, so we will come to that point later, right? And another thing is linear region of operation. So linear region operation is VGS is more than VTH, right? So your transistor is on. That means we have inversion layers. I mean, inversion layer at the surface. VGS greater than VTH, but your VDS is less than VGS minus VTH. That is overdrive voltage. Your VDS is less than overdrive voltage, right? This is linear, right? So this is cutoff. Then this is linear. Then I have last one is saturation. Saturation here, right? So here your VGS is more than VTS again, but your VDS also more than VGS minus VTS, right? So this is the saturation. So these are three regions of operation of a MOS transistor. One is cutoff, when VGS is very less, right? That is cutoff. And linear region is VGS greater than VTS and VDS is less than VGS minus VTS. That is the linear region of operation. And the saturation is VGS greater than VTS and VDS greater than VGS minus VTS, right? So if I go back to the equations, right? So if I go back to the equations, your ID is mu Cox W by L VGS minus VTS into VDS. This is my universal equation, and this is the equation that I derived, right? So, right. So when basically you could see here when VDS is small, right? If VDS is small, right? Let's say VDS is small, right? VDS is very small, right? If VDS is very small, I could neglect half VDS square. Half VDS square could be neglected, right? If VDS is very small, then half VDS square could be neglected, right? And my drain current will be mu Cox double by L VGS minus VTS into VDS, right? So this is so if you see your ID is a linear function of VDS, right? So ID is a linear function of VDS because if your VGS is constant, right? If your VGS is constant, so mobility is constant, Cox is constant, W and L, and VGS minus VTS is constant, right? So ID is a linear function of VDS, right? That's the reason you have linear region of operation. We call it a linear region of operation, right? So here means uh, so if you see um, here so your ID or you could write that your VDS by ID, this is the we call it the on resistance of the this is the on resistance, right? The resistance of the transistor, this is the on resistance of the transistor, MOS transistor. So this is nothing but 1 by mu Cox W by L VGS minus VTS, right? So on resistance, always you measure in the linear region when your VDS is very small, right? So if somebody tells you, okay, what is the on resistance of a MOS transistor? So you will apply a very small VDS. Generally, what you will take the transistor, then apply VDS of around 50 millivolt, right? And measure the current, right? Then we take the VDS by ID. Then it will give you the on resistance of the transistor, right? So on resistance, so when you're calculating the on resistance of the transistor, that means your transistor is operating in the linear region, right? Here, so this is there is a linear relationship between ID and FD and VDS, right? So if I go back to my here, right? So right, and if you look at this equation, your resistance, right? So on resistance definition is when your VDS is very small, right? But this on resistance can change with VGS minus VTS, right? So basically, again, I just missed something here. So when you're calculating on resistance, your VGS is VDD, right? So your on resistance is the resistance of the transistor uh, when your VGS equal to VDD, right? But your VDS is small, around 50 millivolt, let's say, right? So this is the on resistance of the transistor, right? But the resistance of the transistor, if you look at the resistance of the transistor, your resistance of the transistor is a function of VGS, right? So in this region of operation, so basically, if you see, if I plot ID, if you plot ID and VDS, and if you have some here, so this is VGS minus VTH, right? This point is VGS minus VTH means I am operating, right? So in this condition, in this way, so if you see, you could linearize your uh, and this current is a function of VGS minus VTH, right? So current is a function of VGS, right? Let's say this is VGS1, this is VGS2, this is VGS3, this is VGS4, right? So your current will become a function. So this region we call the voltage controlled resistor, right? So like the saturation region of your bipolar transistor. So this region is we call the voltage controlled voltage controlled resistor, right? So your transistor is operating the linear region, but your resistance is a function of your gate voltage, right? That means I could control the resistance of the transistor by changing the gate voltage. So you see the so you have R1. This is also a function of VGS, right? So your resistance will change with VGS, right? If you go on increasing VGS, your resistance will decrease, right? That means your conductivity of the channel increases, conductivity of the transistor increases, right? So this in this region of operation, your transistor behaves as a voltage controlled resistor. Um, okay, so but if you look at this, right? So if your VDS is small, right? So again, I could come back to this, right? I just write down ID mu Cox and W by L, VGS minus VTS times VDS, right? So if I see, so here I could separate into two part, Cox, W Cox, VGS minus VTH, and mu VDS by L, right? So this is the same equation, right? So again, if you see, as I told you, right? So if you look at this part here, right? If you look at this part, mobility times VDS by L. Right? So when your VDS is small, right? So if I come back here, right? So if I look at this equation, let's say your VDS is only 50 millivolt. That's a very small voltage I'm applying here, right? If I'm applying a very small voltage, right? So what is the so your channel is uniform, right? And what is the voltage across the channel is VDS. What is the electric field? Electric field EY here will be VDS. EY is VDS by L, right? And your drift velocity will be mu times VDS by L, right? Right. So this part is nothing but your drift velocity, right? Right. Okay. And if you look at this part, right, your channel is uniform. What is the average charge? Average charge is Cox times VGS times VTH, right? Because your source side is also Cox times VGS times VTH. Your drain side is also Cox times VGS times VTH. So if you take the average charge is Cox times VGS times VTH, and if you multiply by W, this is the total charge, right? So right. So this is so here if you look at this part here, this is the inversion charge, right? So this is the inversion charge, right? So means we are also getting, right, your current is nothing but your charge into velocity, right? So you could quickly derive it, right? So basically this is not very hard, because if you know what is the inversion charge and if you know the velocity, you could write down the equation very easily, right? So this is the equation we are talking about. Similarly, right? So this is my equation, mu Cox double by L, VGS minus VTS, VDS minus half VDS square. So I told you earlier, so if VDS greater than VGS greater than equal to VGS minus VTS, then your current ID remains constant, right? ID remains constant, ID does not change, right? So that current will be ID will be mu Cox double by L. It just replace with VDS by VGS minus VTH. So right, so I could, because your current remains constant, so this will be square, and this will be nothing but mu Cox double by L VGS minus VTS square divided by 2, right? So this is the uh, this is the current in saturation region. In saturation region of operation, your drain current equation will become this equation, right? So this is the first order equation. So mu Cox W by L, Vgs minus Vts square by 2, right? But here you see your ID is independent. ID is independent of VDS, right? Right. That means your drain current does not depend on VDS. It just depends on VDS, right? So this behaves like a current source, and that current source, the value of that current source could be changed with VGS. So that is a voltage controlled current source, right? So in this region of operation, your MOS transistors behaves like a voltage controlled current source, right? So here again, if I look at this equation, right? So if I look at this equation, right, mu Cox double by L, VGS minus VT square, there is a half here. So I could also divide into two parts. So half double Cox VGS minus VTH and mu times VGS minus VTH divided by L, right? So this is the same equation, right? I just separate into two terms, right? So if I copy this, so see, when the transistor is in saturation, right? When the transistor is saturation, that means your transistor is pinched off, right? The transistor is already pinched off, and when the transistor is pinched off, what is the voltage across the inversion layer? Voltage across the inversion layer is VGS minus VTS, right? And what is the field? VGS minus VTS by L, right? And what is the velocity? Will be mu times VGS minus VTS by L, right? So this basically is nothing but your drift velocity, right? It's nothing. This is basically your drift velocity, right? Right. And again, coming to the charge, right? So the charge on the source side, right? V zero. Sorry, Q inversion 0. So Q inversion in the source side is W Cox VGS minus VTH, right? Right. Q inversion at the pincher point is 0, right? So what is the average charge? If I look at the average charge, is nothing but half W Cox VGS minus VTH, right? Right. So this here is nothing but inversion charge, right? See again, your current is inversion charge into velocity, right? So this also comes to the same equation, right? So like this equation here, this is means in the linear region also inversion charge into velocity, right? In the saturation region also you have inversion charge into velocity, but the velocity and inversion charge terms are changed, right? And this so this because your channel is pinched off, right. So if you see in the saturation, your velocity, the electrons are moving with a velocity. Drift velocity is independent of VDS, right? So actually, if you have a channel and you are applying VDS across the channel, that means your velocity is increasing with VDS in the beginning, right? But then the moment your channel is pinched off, your velocity remains constant. That velocity is mu times VGS minus VTS by L, right? Right. Similarly, your charge is also becomes half times WCX VGS minus VTS because your channel is pinched off. So one side you have very high charge, other side you have zero charge, right? And you have a linearly reducing inversion charge. Right? So your drain current becomes same, right? So your current is always charge into velocity, right? And you could get it in this. Okay, so any questions here from anybody?
Sir, here we have written Q inversion as W times COS VGS minus VTS. So, sir, it is coulomb per centimeter.
Yeah, this becomes coulomb per centimeter because
So,
W, because then L is not taken into account here, right? So basically, if you want to find the coulomb, then you have to multiply by L.
so, sir, our current equation is also ampere per centimeter.
No, no. So 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 if you see, okay, so this becomes coulombs per centimeter, right? And this becomes volt per centimeter, right? Right? Your drift velocity, sorry, drift velocity into mobility is centimeter square per volt second, right? 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 So if you see, uh, uh, your or you could think in this term, right? So your current is charge into velocity. This is your current, right? So charge, I am talking about coulomb per centimeter, right? Because I multiply by w, and the velocity is centimeters per second. So this will be coulomb per second, and coulomb per second is nothing but your ampere, right?
Yes, sir.
Right? And means otherwise you could also do coulomb per centimeter. If you took at velocity is mobility is centimeter square per volt second, and then volt per centimeter, right? So this also becomes coulombs per second, right? Right, and this will become ampere, right?
Yes, sir. And sir, can you please go back to the diagram?
Hmm.
Sir, here, as we said, at pinch off, our inversion layer is going zero,
Hmm.
but we have derived current on the basis of average charge. So,
No, I have not done. Means this is just a intuition, right? So whatever we have done means this is just a intuition, but actual current equation is I have already derived earlier, right? So this means we'll get this equation by some definition, right? Right. But means see, this is just a intuition. Once you have derived the equation, then we could get it in terms of charge into velocity, right? But you never, let's say you are told to derive the current, you will derive actually how you derive, we have derived, right? Taking a small, then integrating from 0 to L, right?
yes, sir. But sir, I'm just saying, if our inversion charge is going zero, how is my current flowing?
Oh, okay. So, okay, sorry, I forgot to mention this part. So basically, see, you see here, if you look closely here, so here I have a voltage of VGS minus VTH, right? Right? And I am applying a drain voltage here, right? So there is a voltage difference between these two points, right? And that voltage difference is VD minus pinch of voltage, right? So and this delta V here is your drain voltage minus pinch of voltage, and this length is very small, right? So this delta L is very small. So you have an electric field which is Vd minus Vp by delta L. So you have a very high electric field present here, right? This so basically this point here you have a very high electric field, right? So since you have very high electric field, so the moment, so basically, so you could think of a bipolar junction transistor similar way, right? So in a bipolar junction transistor, what is happening? Your electrons are diffusing from base emitter junction to base collector junction. The moment they reach base collector junction, they just pull to the, because there is a very high electric field across the base collector junction, they are pulled to the other side. Exactly same thing happens here, right? So since you have a very high electric field, so the inversion layers just move by the influence of this field, right? Right. So
Yes, sir.
yeah, so that is yeah. So you see, the moment your charge becomes less, right, to maintain this current continuity, right, current is charge into velocity, right? So if your charge is reducing, that means at that point, at that y, your velocity will be very high, right? So that means your electric field is very high, right? So if you plot the lateral electric field from the source side to drain side, you'll see that your lateral velocity, or sorry, lateral electric field will increase from source to drain side, right? And similarly, your inversion layer, inversion charge will also reduce from source to drain side. So that charge and velocity is constant.
Yes, sir.
Yeah. Okay. Anybody else? Any questions? No questions? Okay, so it's fine. So basically, if I write down the equations here, mu Cx W by L VGS minus VDS minus half VDS square. So this is a linear region of operation. That means my VGS is greater than VTH, but my VDS is less than VGS minus VTH, right? Right? Okay. And I have another equation, so which is mu Cx W by L, here half VGS minus VTH square. So this is VGS is greater than threshold voltage, and your VDS is also greater than this one, right? Okay, so this is my saturation region of operation and linear region of operation. So you see the here there is a common factor which is the threshold voltage. So threshold voltage is we have means threshold voltage uh, is a function of your Na, your Tx, because if I write down your threshold voltage, we know that this is flat band voltage plus 2 psi b, right? 1 by Cx. So I could also write down 2 epsilon Si Qna times 2 psi b. So this is the threshold voltage, and threshold voltage is a function of your doping and oxide thickness, right? Uh, so by changing the threshold voltage, you could change the current, because right, and threshold voltage could be changed by changing the doping, right? Okay, so here see when a transistor so basically let's define, right, when that so we are talking that transistor is off, right? So your transistor is off state. Off is, we always tell, okay, VGS should be 0, right? But not only VGS should be 0, so your VDS should be VDD, right? So this is the definition of off state, right? Off state of the transistor, because most of the operation, most of the circuits you see, when your VGS is equal to 0, that means your transistor is off. But VDS is not any VDS, right? VDS is mostly VDD, because that when the transistor is off, right, your it has to support a whole VDD across it, right? So your I off, your off current, right? When you off current is nothing but the your current when your VGS is 0 and VDS is VDD, right? This is a very important definition, right? So off current of a transistor is a single current, right? Off current of a transistor is a single current. You cannot have multiple off currents of a single transistor, right? And the definition of off current is the current of the transistor when you apply gate voltage 0 and drain voltage VDD, right? Whatever current you will get is the offset of current, right? Similarly, when you're talking about on current, when the transistor is on, that means your VGS equal to VDD, right? So the transistor is on means I applied VDD, and your VDS is also VDD, right? And your transistor is operating in saturation, right? So your on current will become, so this current is I current when both the VGS and VDD, VGS and VDS both are VDD, right? And that is the definition of on current. And on current is again, on current is a single quantity of transistor. You cannot have multiple on currents, right? Of a transistor. When somebody asks, okay, what is the on current of this transistor? You just take that transistor, apply VDD, means apply VDD as gate voltage, apply VDD as drain voltage, then you measure, and whatever current you will get is your on current, right? And your on current is all, means if you see the mu Cx double by L VDD minus VTH square, right? Right. So this is the equation of the on current. So I'll also come to the equation of the off current later, because we have not yet gone to what happens in the weak inversion when the VGS is less than VTS, how to derive the current for that, right? Right. So the on current is half mu Cx double by L VDD minus VTS square, right? And on current is a fixed quantity for a transistor, right? And on current tells you when the transistor is on, how much current it gives. Off current tells you when the transistor is off, how much current it gives, right? And ideally, this I on by I off, right? So I on by I off um, should be infinite, right? Ideally, right? Because when the transistor is off, it should not conduct any current, right? But this is not true for MOS transistors. Even if your VGS equal to 0, your gate voltage is 0, there is a finite amount of current flowing, and that current might be very less, but there is a current flowing. And typically value of I1 by I off is around 10 to the power 6, right? Around 10 to the 6, right? So if your I1 by I off is more than 10 to the power 6, it's a very good transistor, right? It's not infinite, but around 10 to the power 6, right? 10 to the 5 to 10 to the power 6, right? If you want to design a very good transistor, you have to make sure that on current by off current ratio should be more than 10 to the 5 or 10 to the 6, right? Right. Okay. So, so this is on current and off current, right? So again, the because your on current and off current, right? Both of these currents are functions of threshold voltage, right? Right? Your function of threshold voltage, right? So if you look at, because we have not gone to the off current equation, I will not go there. But if you look at the on current, your on current is a function of threshold voltage, right? VTS, right? So we have different devices. So basically, let me write down VDD minus VTS square, right? So let's say if I'm talking about 180 nanometer CMOS technology, right? I know that your VDD is 1.8 volt, so 1.8 volt. When the oxide thickness is 3 nanometer, right? So for transistors, if the oxide thickness is 3 nanometer, your VDD you could apply is 1.8 volt, right? So your on current in this case is mu Cox W by L 1.8 minus BTS square, right? Right. So here you see your Cox is also fixed because your Tox is 3 nanometer, because Tox is designed such that it could handle that electric field. So in this case, right, so if you want to increase the on current of a transistor, the only way to increase on current of the transistor is increase W by L ratio. So which designers generally do. If you need higher current from a transistor, you increase width of the transistor or decrease length of the transistor, right? Or you change the threshold voltage, right? So, but threshold voltage of the transistor, you need to do it by changing the doping, right? Changing doping, right? So this is the only way, because your oxide thickness is fixed. You cannot play with oxide thickness, right? And your threshold voltage only depends on Na and oxide thickness. Oxide thickness is fixed, so you could change it by changing the doping. So that's the reason during device design, you make sure that you have different transistors with different substrate doping. So that will give you different threshold voltage, right? And based on that, we have different transistors in a particular technology. So if you open any PDK, right? Let's say you 180 nanometer UMC PDK or any PDK, so you will see you have transistor starting from, so you have a regular VT transistor, right? You all again has a low VT transistor, you have high VT transistor, you have super high VT transistor. So sometimes we have super low VT transistor and sometimes we have zero VT transistors, right? So there are different transistor flavors we get in a technology, right? The only difference is changes in the change in the doping, right? So only thing which is changing here is the doping, right? So regular VT transistor is your normal transistor, regular VT, right? So if you are getting, let's say, VT of around 0.5 volt here, high VT transistor will give you 0.7 volt, and SHVT transistor will give you 0.9 volt, right? Right. So if you want to design a high VT transistor, you just use an additional implant, additional doping, to make high VT transistor. You need another mask, right? Similarly, super high VT transistor, you need another mask to. So RVT, if you have RVT, so RVT plus one mask here, right? And RVT plus another mask will give you super high VT, right? So low VT, that means your doping is low. So you actually compensate doping, right? Again, you need one mask here, right? So let's say you have put some p-type doping. So you have to compensate that doping to reduce the net doping, right? And you can compensate if you have p-type doping. If you add some n-type doping, then your doping will reduce, right? So that means your RVT will become low VT, right? So you have a regular VT transistor, you add one more mask, it will become low VT. And similarly, if you go to super low VT and zero VT, then actually zero VT transistors, you do not implant any VT, right? So basically, they're all additional masks, right? You have to compensate, right? So means if you have a technology flavor which provides you lot of VT devices, with lot of different threshold voltages, that means you need lot of different number of masks, right? Your mask count will increase, right? So similarly, see, this is for the NMOS. Similar for the PMOS, we have also different transistor VTs, right? Different VT transistors. Again, in any technology, you'll see you have two oxides, right? So in 180 nanometer technology also, we have two oxides flavors, right? 1.8 volt and 3.3 volt, right? So actually every technology provides you two oxide thicknesses, right? And in 180 nanometer case, this is 3 nanometer and this is 7 nanometer, right? And this is typically because you use these transistor 3.3 volt transistors to design input output devices, because input output devices should be able to handle more voltages, right? So that's the reason you use 3.3 volt transistors there. And the normal operational digital or analog transistors use 1.8 volt transistors, right? And since the oxide thickness is 7 nanometer here in the 3.3 volt case, right, your threshold voltage will be higher, right? So threshold voltage will be higher even if they have the same doping. If they have same doping, so 7 nanometer transistors will have higher threshold voltage, right? So these are the things available in a technology, right? You will get to know about it later. Okay, so I think